Testing 1, 2. Test. Test. Yeah, green. Oh, it's working. Test. Test. Good. You want this view or the step? Good, this one. Okay. Yep. Marker. Oh.
So pointer. So
you can use it too.
if it works. Yeah. Yeah.
But it doesn't move the slide, right?
Which
I don't have enough pulse here.
Oh.
Next up.
is there oh, okay.
Okay, so I guess we can start.
That's fine, cause
I'll just stay here. I'll just stay here now.
yeah, I'm gonna do the same thing because I'm a.
Okay.
You want me to?
Yeah, so like.
So I'm gonna be behind him.
Okay.
Be behind.
Yeah, if someone actually answers a question, we just give them something.
Yeah.
All right, so welcome everyone. Today we'll continue with the student presentation. Welcome those watching us on YouTube. I guess we can take questions from those who are watching us online. So please feel free to leave your question on the chat so we can take them on time. We will have some time for discussion toward the end of the talk. For today, we'll have 2 interesting papers. So yeah, whenever you're ready, you can start.
Okay. Hello, everyone. So today we'll be presenting, Copy-on-Flip, Hardening ECC memory against Rowhammer attacks. So this is a very interesting paper that was presented at the Network and Distributed System Security Symposium in 2023 by researchers at Intel and then a university in Amsterdam. My name is Prince.
My name is Khalil.
And without further ado, we'll just get right into it. So first of all, we're going to start with like an executive summary of what our paper is about. So to give you a bit of context, right? So Rowhammer, ever since it was discovered in 2014, it has still been threatening DRAM, and even like, certain hardware differences that have been actually implemented to sort of like cater for it, such as the ECC memory, can still be exploited as well. Another problem is the fact that even though there has been like hardware and software defenses that have been like sort of like implemented to sort of like curb like Rowhammer, these fixes are either costly, heavy, or impractical, right? Basically, they sort of like cause a lot of like system overhead. So our idea is not to reinvent the wheel, but rather use ECC's correction events as an early detection of Rowhammer events, right, or Rowhammer attacks. And our approach actually includes, first of all, detecting whether like a bit flip is going on. And we'll also talk a bit more about like what all these machine check exceptions are, right? So once we detect that a bit flip is ongoing, right, we can assume that that could be a Rowhammer attack. We will just migrate and then offline those pages, right? So you could assume a page is like a portion in memory, right? The OS doesn't see the physical memory, it only see pages, right? And then that will sort of like protect both the data, which is like the user, and then the kernel memory. And by using like Copy-on-Flip on your like commodity servers or like your systems, what you do get is you get like a 95% attack surface reduction, right? So that means it is a very comprehensive solution. And also there is less than 1.5% like runtime overhead. So it's very lightweight as well. And in the case of like intensive input and output heavy load, the runtime overhead goes up to 11%, right? 11 as well. And then, so what will be the takeaway from this paper is the fact that COF, or copy on flip, is actually practical. It is low cost. You don't need much to do. You just take the code, you just put it on your server, and you just run it. It is also low memory overhead, and in the end, it is also effective. But before that, who knows what Rowhammer is here? Exactly, right? So look at this analogy, right? You give him one cookie. So imagine two neighbors, right? So this is Andy, this is, let's say, Margaret, right? They both work at Amazon, right? And we all know that recently Amazon has been doing a lot of layoffs, right? And layoffs do hurt because you know that you're waking up the next day to work, but then you get an email saying, can you please check your email before coming to work because your access has been revoked and you're getting laid off, right? So then Andy and Margaret, after getting that layoff email from Amazon, they get furious. So what do? They start hitting against like the walls, right? Because they are up like neighboring, they are neighbors, right? So they just start hitting against the walls. And then this beautiful picture of Mona Lisa that was like hanged in the middle just falls down. So as he said, it's basically like Rowhammer is a case whereby you sort of like activate rows or neighboring rows, causing a bit flip in an adjacent row, right? So that'll be the definition for Rowhammer: repeatedly activating memory rows, right? Causing bit flips in adjacent rows. And we all know how the memory works, right? Like every DRAM cell has like a capacitor, a transistor. The capacitor stores the charge, which is either 1 or 0. So when we say a bit flip here, it's basically like a 1 turning into a 0 or a 0 turning into what? A 1 due to repeated activations of those memory rows. So we're gonna do a simple exercise here, right? So assuming there's an attacker, right? And we have our DRAM cells here, right? And then we know that the victim row, this is the row the attacker is interested in, which is row N, right? Oh, okay, that was a flip, but yeah. So basically what the attacker can do is they could try to activate these rows here. So N-1 and N+1, right? So these are like the neighboring rows, right? So what do you think will happen in this case? So the more they do that, right, it gets to a point whereby one of the charges here, right, might leak from 1 to a 0, because we know that capacitor leak charges over time, right? So the more you sort of like activate these rows, it might cause like interferences that might cause the charge to leak a bit faster, right? So basically, a 1 could turn into a 0, right, before the next refresh. Because we know that in refresh, what refresh that it just copies the row and then writes it back, right? So that could cause like a bit flip with those continuous activations. So yeah, there's a case of Rowhammer. But let's look at the other scenario. So we have the row, the victim row here, and then we have these two. So we sort of like, the attacker sort of attacks the N+1 row and an N+2 row. Do you think this can result in a Rowhammer attack? Anyone? I mean, we said that like Rowhammer is, basically like, repeatedly activating neighboring rows, right? I mean, these are neighboring rows, but then do you think it could actually end up in like in a Rowhammer attack or a bit flip? Actually, yes, because recently there's a paper by Google called Half Double, right? And they proved that even in a Rowhammer attack, you don't actually need to sort of like activate neighboring rows. You could actually activate distance rows, and you might still be able to cause a bit flip in the row of interest you want, right? So it looks like Rowhammer is a very interesting topic that researchers hop on it and then try to find like, interesting ways of sort of like flipping bits in memory, trying to let us know that it is a very important like vulnerability in current DRAMs. So now why should we care? Can anyone give me a scenario, or like in which sector, right, in our life do you think Rowhammer could be fatal? I mean, I'll give you one example. For example, your bank account, right? You have $1,000 in there. One day you wake up and it's 0, right? Because $1,000 is basically binary numbers in memory, and these are ones and zeros, right? So if someone is able to flip a lot of those bits, right? Now the $1,000, which is represented as a binary number in memory, is now what? A 0, basically 3-bit flips, right? So that is one scenario. in the banking sector. Can anyone give me any other example of like any sector whereby like Rowhammer could be disastrous? Exactly, adversarial attacks, right? I could say that is something like that, right? Because, oh yeah, you could give it one cookie. Yeah, does anyone know any other like, scenario case whereby like Rowhammer could be fatal? I mean, I could just, go on. So like, let's say in cloud as well, right? We all have our data stored somewhere in data centers all around the world, right? So if I'm an attacker and I do want, let's say, Naheem's like data, right? And I know that it's stored on a server somewhere in maybe Portugal, right? And all these servers are just made up of memories, right? Memory, DRAMs and all that. I could just launch an attack in there, flip a few bits that would allow me to access your data, right? And I could put it on the internet, but I wouldn't do that. Next in line, we have in aviation as well, right? For example, this is a bit tricky, right? Imagine you book a flight from Dubai to Los Angeles, LA, right? But then somehow, because memory, like the planes are also equipped with memory, right? Because it needs like the coordinates, there's autopilot and there's all those things, right? So imagine if someone is able to sort of like flip bits in that memory, and let's say the coordinates change from Los Angeles to, let's say, Malawi. So basically you book a flight from Dubai to Los Angeles, but then you end up in Malawi, right? So basically bit flips, like bit flips are actually a serious thing in like current DRAMs. Well, we're also gonna look at a bit of like Rowhammer attack evolution. So basically it was discovered in 2014. Later on, attackers also showed that you could sort of like induce Rowhammer through the browser, so JavaScript, right? And then later on, they found that you could do many-sided Rowhammer attacks. So basically like activate several rows through the browser and still get a Rowhammer attack. Also, there's half double, which I talked about earlier. And then there's also true like adversarial observations on federated learning clients. But I do want to ask one simple question. We've learned a lot about memory in class, right? We know that anytime you sort of request data from memory, right? It fetches the memory, it fetches the data, it puts it in the cache, either L1, L2, L3, right? So why is it that attackers are able to sort of like activate these memory rows? Because when they first try to fetch the row, right? It fetches the row, it puts it in the cache. So on the second call, it shouldn't hit the memory, right? It should just hit the cache and return. So why do you think they're able to launch these Rowhammer attacks? Because they shouldn't be able to sort of like get like or activate one row several times, right? Because there's a cache, right? So what do you think they do? What do you think attackers actually do in this case? To sort of cause several cache misses. What do you think they're going to do? Anyone knows the answer? I mean, it's what? A bit close. I mean, you could just flash the cache, right? Because once you flash it, then the data isn't there anymore. So the next call you make, it goes right to memory, right? It returns. What you do again, you flash the cache. So that is how Rowhammer attack, like you basically like simulate a Rowhammer attack, right? You get a call, it returns, puts it in the cache. In your next call, you flash the cache. So it hits the memory all the time. And then once you do that repeatedly, at a point in time, you may be able to flip a bit in memory. Next up, so the ECC memory, right, was thought to be like an initial sort of like solution to Rowhammer. I mean, first of all, it wasn't actually made for Rowhammer. ECC was made for the fact that there could be bit flips in memory, right? That is a natural occurrence. Bit flips can actually occur anywhere in memory, right? But that's a natural occurrence. Rowhammer is actually human induced, right? So ECC was made for the fact that, okay, bit flips could occur. So we need something in place that could actually correct bit flips. And has anyone here see like an ECC RAM before? Can anyone tell me the difference between this, an ECC RAM, and then an ECC RAM here? Do you see any difference? What is the difference here? Yeah, there's an extra chip. You can get. Oh, Naeem? Ah, too much. No. So you see there's an extra chip here, and what this extra chip does is it sort of like stores like priority bits for all the data on the RAM, right? So what happens is before it actually, let's say someone requests data, right? The priority bits actually checks if the data, has there been a bit flip, right? If there's been a bit flip, it is able to what? Correct it. And it does that through like some sophisticated mechanisms, like I think for Hamming code, right? Basically, every ECC word here on the chip is like, let's say 64 bits, right? And every 64 bit has like an extra 8 bits that stores like the priority for that word. So that will be used to sort of calculate, has there been a bit flip in any of these positions here, right? And then it will correct that bit flip. So the full name for ECC is like error correcting code memory. And it follows a single error correction and double error detection, right? So let's look at an example here. So first off, this is the DRAM cell, right? There is one bit flip. Do you think the ECC will be able to correct this with just one bit flip? Yes, right? It would auto correct it. And what about in the case of 2-bit flips? Do you think it will be able to correct it based on the name? Single error correction, double error detection. Do you think ECC will be able to correct these 2 bits? Yeah, no, because well, it can't. Like that wasn't its function. It was only made to correct a single bit and be able to detect what? Double bits, not correct it. So this will sort of like result in a system crash, or the system could panic, your system could reboot, or any other thing. But in the year 2019, right? You know, researchers are very smart. They always find ways to break things, right? You create it, they're like, nah, I think I could find a way around it. So in the year 2019, there was a paper called ECCploit, which sort of said, okay, we know that the ECC can actually correct bit flips, but then there's a way to bypass the ECC, right? So what do they say? They are saying, for you to bypass the ECC, right, you need to have 3 bit flips at a time. But then in launching a Rowhammer attack, you usually have to sort of like find a spot in memory whereby you could flip 1 bit, right? And then find a spot in memory where you could flip 2 bits, right? So if you do that like sequentially, you might end up getting like a 2-bit flip, and then ECC might detect it, right? So what they're saying here is, instead of doing that, first try to find space in memory that you could actually flip bits, right? So let's say you find a bit flipped here, you find a bit flip here, you find a bit flip here. Now you know points in memory, 3 places in memory where you could flip a bit, right? And in your final attack, what do? You flip all those 3 bits at the same time. So now there are 3-bit flips, not 2-bit flips. So you've actually bypassed the ECC function. So that is called like 1 bit at a time templating to bypass the ECC function. And if you want to read more about the paper, we have the QR code there. And we're also going to talk about a few more like hardware level defenses. So beyond the ECC things that have actually been proposed. So we have Blockhammer. So Blockhammer says, okay, we're going to track the rate at which like rows have been activated, and we're going to use that to sort of like block those rows repeatedly. There is like randomized row swap. Who has an idea about what this is doing? Just from the name, randomized row swap. I mean, basically Rowhammer means you're trying to like activate cells, right? So randomized row swap is basically like, let's just randomly put the rows around, right? Just to avoid one row being repeatedly activated. And then there is Panopticon as well. But then the issue, okay, I already, but here, there are some issues with all these hardware level defenses, right? Because imagine you buy, let's say, an Elantra, right? And then there is an issue, right? What does the company do? They sort of like recall all the batch, right, that is sold, right, of Elantra, right? And they try to fix it, but then how long does that take? Do they fix it in a day, or it takes a longer time, all right? So the issues with like hardware level defenses is the fact that sometimes you can't just fix something and it'll work for everything, right? So you can't just put like all these hardware level defenses and it will work for every entire server out there. Also, some of them are bypassable or costly, and then it takes years to patch, right? And also it's costly because you need to go to a lab, you need to put things together, fix it's all like labor intensive as well. But beyond that, we also have like software level defenses, including RIP, RH. I mean, I'll just move on, Zebra, RAM, and then like SoftTRL. But then these also have their own sort of like problems, right? For example, if you look at SoftTRL here, it only protects against page tables. And let me remind you, the OS doesn't see physical memory. It only works with pages, right? So this one only protects against page tables, so it's incomprehensive protection. You could also have like significant overhead due to, for example, let's say allocating more memory and all that. And then it also sometimes requires complex system changes, right? And that brings us to our solution of the day, which is copy-on-flip. And then I'll pass it over to Khalil to get right into it.
All right. So I want us to start off with thinking, right? I'm going to ask y'all a quick question. And if you get it right, you get some cookies. All right. So how can we improve the use on ECC? Prince talked about the mechanics of ECC and how it works. How do you think we can improve just the basic functionality of ECC? Any takers? Multiple bits, like extending the bit checking. Okay, you agree? Okay. Yeah, you give them, yeah. All right. So I want y'all to look at this picture, right? Imagine this is Hartsfield-Jackson Airport. I know a lot of y'all hate Hartsfield-Jackson Airport, right? But imagine this flow of traffic basically being Rowhammer. So these two people, you have thousands of people coming into Hartsfield-Jackson Airport on a day-to-day basis over and over again. And a lot of them do not have luggage that could just go through the systems right here, these scans right here, without being detected, right? So imagine these people are going to be Rowhammer itself. You have thousands of people coming over and over again with bag luggage over and over again. These are the aggressive rows being attacked, right? What we're going to do with this is these systems over here and this nice lady right here is going to be ECC itself, right? So we're going to use this as early detection, right? So we're going to scan all of their luggage right here, over here, and use ECC as early detection. So the way this works, say I'm this person right here. Say I have something bad in my luggage that's not supposed to be there. Maybe something metal, right? And these scans go off. We're going to simply tell that person, hey, you cannot keep that. You're good. Keep on going through. That's one thing. But what if they have multiple things? Now we need to go to this guy right here, which is going to be what? COF itself. So this is where the basis of COS functionality basically comes into play. All right, so introducing copy-on-flip, right? So the core idea of copy-on-flip is to use ECC as early attack detection. And then we're going to have functionality in copy-and-flip to be able to migrate these vulnerable pages and then also offline them. And I'm going to go into more detail about that later down. The key contributions in the design and implementation, it only takes 600 lines of code. So it's very, very easy to implement in our systems today, right? We have it being able to be deployed across all systems that have ECC within their memory controllers. There's our open source GitHub right there that actually has all of this code and the functionality if y'all want to go look at it. And then, like Prince mentioned before, it has an attack surface reduction of a little over 95%, which is incredible, right? That's the whole goal of this. And even with that attack surface reduction being reduced, we only have little to no overhead, which I'll go into the metrics a little later in the slides, right? All right, so I have a question for everybody about the assumptions that we can make. What can we assume an attacker can do and has access to during a Rowhammer attack? He can steal sensitive information? How, though? Like, how does he have? There you go. So that's good. You can give if they don't have it. Yeah. So there's four main things, right? We got to assume that the attacker can trigger these bit flips at will, right? We got to assume that the attacker has access to these aggressive rows in memory and can target a specific row in memory and trigger these bit flips at will. It's able to do this. That's why I wanted to go more in detail. It's able to do this to be able to allocate and deallocate memory, right? That's how it's able to trigger these bit flips. Also, one thing that an attacker has on its side is time side channels. So this is basically time data sensitive to our system. Specifically for ECC, it tracks how kind of how quick a flip is corrected, right? So is it simultaneous, and it tracks it in nanoseconds. So it has that information able to be located as well. We got to assume that the attacker knows ECC's functionality in general to be able to buy. At this, we need a system with a memory-based controller that has ECC. This is how copy and flip can be utilized in these systems. We need our memory controller to report errors directly to our OSET, our operating system. So copy and flip can be able to read these errors, and this happens via machine check exception. And then we need a server platform with ECC, and our goal is to prevent data corruption, right? All right. This is a very high-level overview of how ECC works. Right here, this works. Right here, you have our Rowhammer code basically being targeted in the ECC of DRAM. So that's how we raise this machine check exception that's being passed directly to the OS of the system, so copy and flip can read it. And now we have to do something about that. So for 1 bit flip, we mark the page for monitoring, right? But what happens if we have more than 1? Now we have 2, right? So what we're going to do is we're going to allocate new physical memory. We're going to migrate that page via this function right here. And then we're going to update that page table information, and then also offline that previous vulnerable page. That's a very, very high level of how the functionality of copy and flip works, right? So let's see it in action. So as mentioned, Prince mentioned before, you have your aggressive rows adjacent to the victim row. What's going to happen? You have a bit flip that changes it from 1 to 0. We know that ECC corrects that itself. We don't have to do anything about that. But what copy and flip is going to do, we're going to set a flag on this victim row and say, hey, we're going to watch it. We're going to monitor it, right? But now we're watching it and monitoring. Now another bit flip happens from 1 to 0, let's say. So what do we do? What does copy and flip do? We're going to take that entire victim row, allocate new physical addresses for this victim row. And then what we're going to do is we're going to transfer and migrate that data to those new allocated physical addresses, right? But what do we do with this data right here? This victim row data that has been basically row-hammered by the attacker. What do we do with this data right here? Anybody have the answer? Flush it? Okay, that's a good one. Anybody? Recharge? Also another good one. Say because all right, so those are great answers. What we're basically going to do is just completely offline it. That's what copy and flip does. We don't want to recharge it or flush it. We're just going to simply offline it, right? This prevents the attacker from being able to reuse these aggressive rows to victimize this row right here. This, and there's also another attack called reuse attack, hence the name. So this kind of nullifies all that. Now what do we get? We get good, safe memory. All right, so now we need to go into what memory needs to be protected. What do y'all think is the type of memory that needs to be protected? I want to hear from other people too. Same people keep on answering. Right. What type of memory needs to be protected? This whole thing is about memory, the bits being flipped, data being corrupted. What type of memory do we need to protect? Say it one more time. Not quite. Kind of on the right track. It's actually very simple, right? We're going to protect any memory that an attacker can access, right? So basically, how attackers do Rowhammer is that they massage this data for templating, right? So they're able to access this data, they're able to template it by allocating this target memory. So we need to understand the requirements for an attacker's templating. First one is that they allocated target memory at will. Second one is that they must be able to allocate aggressor locations near that target memory. And they must be able to control the victim data for that target memory at will as well. And then that they have timing and memory access to determine whether a bit flip has been corrected by the ECC or not. And then this goes into the specific memory type coverage. So as Prince mentioned before, there's a lot of pages, articles that only protected one certain memory type. The great thing about COF is that it protects multiple. So it protects user pages, which basically stores all of our application data, right? Then we have our page table pages, which holds all of our virtual addresses from physical addresses to virtual memory. Then we have slab pages, which object caches, and this is used for small dynamic allocation. We have vmalloc, which is our virtual continuous memory. We have page caches, which are cache files that hold our user processes. Then we have kernel stacks that are used by per stack, and this holds all of our like system information, system calls, exceptions, stuff like that. And COF is able to provide protection on all of these different memory types. All right, so going into copy and flip's design, we have our templating detector, starts by detecting these pages that occur on a bit flip, and then we have our page detector, which migrates and offlines these vulnerable pages. Going into this, you can see our DRAM. Our ECC and our DRAM has, the memory controller has all access to that information. Then say a bit flip happens, the machine check exception goes directly to the OS error reporting system. This is viewed by COF's templating detector right here. So now if more than one bit is detected, then we go into our page protector component right here. And that's when we start allocating and migrating these different memory pages. All right, so going into the templating detector, right? So this just already leverages ECC itself. ECC is able to correct one bit at a time, and that's it. But it uses what ECC can already do. One key information that this has in the machine check exception is our page frame numbers. So this is very important to see where that memory is, where that victim row data is actually located in our row buffer memory, right? So this is very important to have this information. And these checks are raised almost instantaneously. So COF is able to view this information and do something about it as a Rowhammer attack is ongoing, right? And then going into the mechanism, so it hooks directly to the OS. We do a PG flip flag that basically keeps track of the first flip, and then we'll keep track if a second flip happens and then trigger the protection. So why 2 bit flips? Why do we start basically doing something on COF at 2 bit flips? Can anybody answer that question for me? Why not 3? Why not 5? Why not 10? Why not 1? Why do we start TOS, the main functionality at 2 bit flips? That's good. What about 3 bit flips? What about 5? Why not start the process there? Okay, that's good. Is it good enough?
Maybe later you see someone.
Right. All right, so the main thing is that, as mentioned before, is that ECC corrects 1 bit flip. At 3, it normally just, the system normally just crashes, right? That's the main distress about ECC itself, is that 3 bit flips, if they are flipped simultaneous, the system will just crash. So that's why we need to protect it at 2 bit flips to stop the attack before it can actually happen. So this stops low entropy attacks, and it acts very, very timely. So it acts before the system is able to just crash. The trade-offs is that there is small, slight approximation, but it's little to none. This still ensures that we have protection at the lower levels, so we have great protection over it with little to no overhead as well. And then tracking granularities, right? So we need to know what type of level we need to track these specific bit flips. We have ECC word granularity and we have page granularity. What do y'all think is the level that we track it for copy on flip? It's one of these two. You got a 50% chance of getting the question right. Anybody? All right, we track it at page granularity. The reason why is that ECC word, so bit flips are bound to happen, right? We have tens of hundreds of DRAM. Bit flips are bound to happen, right? If we track these bit flips per ECC word, the granularity is too large. It's too much metadata to keep track of. This provides too much overhead for our system, not making our system reliable, making it run slow, could even cause crashes, right? So we track it based off of page granularity, which is already implemented within our memory controllers itself. They already report by page level. So COF just aligns with that specific reporting level. Simplifies the metadata to a specific flag instead of having all of that high overhead. So now we have lower overhead. Going into our page protector component, we have 2 steps for this. Main thing is allocating new physical pages, copying, and then updating it. The main thing that we have to do, though, and what I really like about copy and flip is that it flushes all of our recent translations. So TLB stands for translation look aside buffer. This holds all of our memory translation locations in a binary format. So what COF does is that after it copies, migrates, updates, it flushes all of this recent translations. And then it offlines that page by marking it as poison by this poison flag, this PG hardware poison flag, removes the allocator. This prevents reuse attacks, and why both are necessary, right? So migration alone, attackers can continuously just keep allocating and reallocating those same memory slots, right? So it's not feasible. But if we just do offlining alone, we will lose so much data, right? So that's also a problem. That's why we have to kind of join them together. And then Prince will go more into the migration strategies and the memory types.
We're gonna look at Hertzbleed side. Also, kind of like passive memory. That's the right. So we have user pages, right? So what they do is very simple. You're just gonna migrate that page, and our page is like virtual first. That's for like page table. So page tables actually store like packets. Once you migrate a page, don't do that. That page cache, I also do the same thing. That page table pages, which called virtual stop mappings. Also, where you do that, you just update the stop references. You have the uncontiguous memory, as well. But here's the thing: these ones are very tricky. You can't just it isn't contiguous. It's kind of all across memory. So how do you sort of migrate that? So it's good. I think one thing I like about the fact that it's like memory. That's not this also similar to, and we have like kernel pages as well. So we're gonna first look at the migration strategy for like the user page. So when Copy-on-Flip text that the page is vulnerable, so let's assume this is a page, right? This page is vulnerable right now, right? But then this page has like it's already mapped to virtual address, but someone that's a page table entry. Page table, right? So what does it do? It allocates a new page, right? So we have a new allocation, copies the data, from this vulnerable page to the new one, right? Have the data copied, it offlines this, and it points to the virtual address here. This is very simple, right? So this for like, and anyone tell me if you know how like copy and flip that for like uncontinuous memory or like malloc. So this is a case whereby the data is scattered all across memory location, but it's not contiguous. This is something. I can write it two ways. Did you plug on multiple things? Not quite. It's kind of close. But so here's the thing, right? Even though like the physical pages are scattered all across memory, right? The actual addresses are actually contiguous. Because when you call vmalloc, right? Vmalloc, anyone here knows C? Then when you do malloc, it just allocates every somewhere memory, right? And the actual address is actually contiguous. What does copy on flip do? So basically, we have the current virtual address pointing to one. This is our vulnerable page here. And we have like P2, right? So we first create a new, we make a new allocation, we copy the data, we offline this page, and then we point this virtual address to page here. So we move the address up pointed to this page, and we put it here, and we offline it. Right, so we offline this page right here. So what of not page cache? This was somewhere on the previous slides. Because not page cache is actually similar to user pages. We do the same thing. Even it's vulnerable, we allocate a new page with like an allocation, copy the data, replace, offline. But let's get into slabs. So slabs, I said, slabs are also similar to non-contiguous memory allocation, right? The thing with slabs is it's actually not migratable. It's because of the kind of like allocator, that's what I allocate this memory, you can actually migrate this stuff like that, right? And a copy of flip finds a way around. What copy of flip does is, so this slab for frame allocator, right? It doesn't allow like this to be migratable, right? So what we can do is we know that non-contiguous memory, right? We can use that allocator, right? Instead of using the slab allocator, right? We switch it or we swap it with a non-contiguous allocator. So now this becomes like the same process that non-contiguous memory use, right? Basically, if there is a vulnerable page, right? Since it's allocated by the non-contiguous allocator, just copy the data, we offline it, find the new virtual address. Okay? And for map page cache, like as the name suggests, it's a map. Like if something is on map, you need it. It is in the cache, but then it's a map. Like you don't need it again, right? What can you do? You just evict it. Just evict it from. We say, okay, this page here is not mapped to anything. Don't need it. So just evict it. Then we have kernel stacks, which is also migratable. Because of the sort of like allocator that allocates like kernel stacks, right? And what was the name for it again? You want to remember? Was in the slaps. Like, I don't know, paying attention, but let's get right into it. So it's the same frame allocator, right? So the frame allocator is like migrate these pages. So what you do is swap with a non-contiguous allocator, right? Let's say this you allocate a new place, copy the data. So basically, that's all copy on flip does. Anytime you text like a bit somewhere in the page, right? Two flips, right? First thing, allocate a new space, copy the data, remap it. And we have page tables, right? So page tables is the actual table that stores that virtual physical memory mapping address, right? Because like I said, the OS doesn't see physical memory, it doesn't know what it's doing, right? It just know about the pages, right? And then the pages to show an idea of the page table, right? And these are stored in the page table. So if you have this in the page table, right? And let's say this page table contains a virtual memory page number, right? So there's a page number 2, right? So if this page is vulnerable, what copy on flip will do is it allocates a new page, copies the data over, right? Update the physical reference, and offline that portion of memory. Right, so basically the same thing again. Allocate, copy, update. But it's a simple question. It's a very tricky one. So as copy-on-flip is sort of like trying to migrate the data, and an attacker flips a third bit before the data is being migrated. So first of all, let's analyze the case whereby there's no copy-on-flip. There's no copy-on-flip. And an attacker sort of like putting a third bit if like let's say there's another solution out there that is trying to sort of like just migrate the data. Right? Without no copy-on-flip. Do you think that is possible? Yes, because I mean, before taking like operating systems, you know that it's mostly like processes, threads, and things like this that runs all these apps, right? So copy-on-flip basically goes into these sort of threads, right? Because these sort of like SFTs or threads, sort of like data. But then our copy-on-flip sort of like solve this, right? Is to sort of pause all user threads, right? Because right now we know that if there's an attack going on, we don't pause all the threads, right? The attacker could race to sort of like check the thread, right? Why don't you just pause all threads, right? Migrate the data and what? Resume all the threads. And so that is how copy-on-flip is. So copy-on-flip, an attacker cannot race to sort of like, into the thread because first of all the threads are blocked. We block all threads. So now even if the attacker is trying anyway, right? It copies the data safely to the new space memory and it compromises it. Or it allows the attacker to say, oh, now you can the page is also offline. Yeah. Next we go into the implementation.
All right, now we're going to go into the implementation footprint. So it was ran on a Linux machine of version was 5.4.1, required around 600 lines of code. Most of these are kernel changes, right? The memory, which it says both related to the migration of vMally, which are default slab memory allocation. And then it was also evaluated on an Intel chip. The specific one is Exxon Silver 110 with 34 gigabytes of DDR4. All right, going into our runtime overheads. These are all of our metrics ran on these different benchmarks. So it was ran on Spec 2017. These are our results, right? So we have our baseline seconds and all of our specific benchmarks right here. And we have our COF seconds right here. And you can see that none of these are over 1%, which actually some of them actually have an overhead of only 0%, right? So it's incredible. Negligible overhead with our geometric mean only being 0.2% of overhead. It's amazing, right? It's kind of what we expected because copy-on-flip does not do any type of changes to our user memory at all because this memory is already able to be migratable, right? Going to our runtime overhead for our web and user workload, this is ran on modular tracking. We have our milliseconds right here for our baseline, and then our COF milliseconds right here. What we can see is that it was tested on Google Chrome, which has a lot of heavy I/O sites, JavaScript. So this is actually tested under pretty harsh conditions. We can see that it's very reliable with a geo mean of only 1.1% of overhead. So it's reliable on systems that are very complex. That's why it was ran on Google, right? Yeah, see that right there with our geometric mean of being 1. So this is our runtime overhead and our I/O saturation. And this is our worst case. So worst case basically means that a Rowhammer attack is actually at play right now. This is data where a Rowhammer attack actually at play. Those ran through Nginx. And what you can see from here is that we have our baseline throughput and our copy-and-flip going right about here. This is our copy-and-flip throughput and our baseline. You can see that we have about 10.56 throughput reduction compared to these, right? It also kept track of our CPU usage in our baseline and our copy-on-flip. You can see it's 1-to-1. So the CPU usage is not increasing with that as well. This allowed us to have a latency increase of 12.6% as well. And this is our worst case scenario. Now, runtime overhead under a Rowhammer attack as well. Now, this is run during the most adversarial stress. So we ran it with a Rowhammer attack having a bit flip every 22 seconds, right? So we can see from this that there's only an additional 0.69% of degradation compared to copy-on-flip's normal overhead, right? We can see that through the graph. We got our baseline throughput right here, our copy-on-flip throughput right here, and we have our medium attack rate versus our maximum attack rate. These are pretty much one, right? What we can conclude is that an attacker cannot abuse copy-on-flip, right? It's not able to just increase the attack rate, to increase the bit flip rate, and copy-on-flip. That's what we do. Now going into our memory overhead, this was ran on multiple DIMMs. These were our most vulnerable DIMMs, right? All of our total flips. And you can see this is the amount of memory that was offline. Pretty much all of these are around 9%, right? But if you look at the entire data, which is very, very long, so I didn't amount, POF actually only offline 1.25 or 26% of physical memory. And then our worst case scenario being only these 5 DIMMs right here being around 9% of offline memory. All right, now let's go into our SWOT analysis for copy-on-flip. The main strength is that it's already leveraging mechanisms. So any type of system that already has place, it's able to utilize it. But it does it one better. It's able to take it to a whole nother level. And this allows us to protect like a wide variety of memory types, not just one memory type, but we have migration set for a lot of different memory types, right? Then it also shuts down an attacker template base altogether. One of the main weaknesses that we discovered is it still has DOS exposure, which is denial of service attack. The reason of this is because we can't track whether a bit split happened on that same specific bit or a different one, right? We have no tracking of that. POS does not know that. So what an attacker can pretty much do is that they can keep targeting this same bit flip at only one flip. So keep targeting each error correction over and over and over again. So now for POS offline this large memory, and it leads to offlining a large portion of our memory, right? Opportunities for this is adding more tracking, which we mentioned earlier, right? So why don't we record the actual bit location, the actual offset of that bit, right? The way we can do this is that error correction codes, they have this thing called syndrome, basically the bit location of that specific bit in binary format. So all we have to do is just keep track of it. Let's send this information to our templating detector that we're already using for copy-on-flip. And the only thing we need to do is just store the information in a separate bit. This will cause slight overhead, but it allows more protection, right? And then one of our biggest threats is our on-DIMM attacks, right? So these are have-level attacks before. And the reason for this is that even newer DDR5 and even some certain DDR4s, they don't have their memory controller itself. They actually have it in memory module. So each specific chip within that memory module has error correction code functionality, right? So each chip performs its own correction, right? The downside of this is that the high level points to the system, and since it's already corrected at the memory module itself, never that information directly reported to the OS, right? But the data never leaves. right? So therefore, copy and flip never reads it. Therefore, a template is never thrown, and it just reads it as it's on. Going to one of our future ideas, right? So machine learning is very prevalent nowadays, especially AI. So why not implement it in copy and flip, right? What we came up with is A-copy and flip, stands for adaptive copy and flip. It has predictive analytics, right? So the way that this works, that we plan on using some type of lightweight machine learning module, like linear regression, that's very, very easy, cost you more overhead, to train it on our direction, right? So we will continuously train this direction data on ML models. And what we would do is come up with some type of probability that's a page will experience second bit flip shortly after that first bit flip occurs, right? So that allows us to not allow that second bit flip occur. Before the second bit flip occurs, right? Well, our main critics on the paper was it's limited to memory controller based ECC. This is bad because what if there's ECC, as I mentioned before, actually in the module for itself. And then there's also, when we offline memory, in our worst case, we're offlining around 9.3% of memory, which can mean a lot. Say you have 32 gigs of memory, right? This is around 3 or 4 gigabytes being completely offline. It doesn't reboot until it doesn't go back online until actually reboot. So there's definitely some need for improvement for copy and flip as well. Conclusion though is copy and flip is very simple, efficient at hardening the ECC. Go against our Rowhammer attacks. It can protect all templating targets for our memory, and it has low overhead with practical. That's all we have for copy and flip. Now we'll get into our discussion time for any questions that we might have, and then we also have. So any questions in the audience? We have our questions if you don't have any questions, but if there's any questions.
There's not much hardware involvement, right? Because I think now entire onus is on software and OS. I think. What's the part of hardware, if you have any introduced in the blog? Is there any part of the hardware that we have looked at from ECC side, or there's no hardware implication on?
On the ECC, no.
It's all software and OS.
Right. That's what makes it easy, like. More questions? So this will also, I mean, we'll need further research on this, but what we can use, like our machine learning model, right? One of the main parameters is how ECP code actually looks, what information is taken to it, as that as a parameter for our machine model.
Now, once you train the model, always like notify all these people, right? So that was another solution that was put by, I think I like random amount full swap. That's a recent.
Who exactly is the attacker that you were talking about? Like, how do you define it? And like, is it like an external program that comes in the system, or like did? Hi. So my question is, I was wondering who exactly is the attacker here? Is it an external program, or how is it exactly getting into the memory? And what's the path of, like, is it an external program, or why exactly some specific rows are getting targeted? And why it doesn't like just remove the entire like data if someone like, I'm just curious to know. I don't know. Yeah.
Even attacker knows C very well, all of that. You can be able to sort of like move all these rows, slash. I mean, if you go like everybody saw like some instruction code, right? We see like blue, slash, and all that. So each one of those, oh, like able to allocate memory like the whole row. So I could get an attack, I could just right? Write some C code that could actually like allocate the memory, able to calculate. Okay. I think it's someone who's very, and also someone to like JavaScript develop, right? So JavaScript doesn't really need a lot. It isn't a low level language, but even with that, I guess I think it all depends on. Attacker could be someone who knows C very well, right? Or someone who
It's like a external system vulnerability is not like specifically related to memory itself, right? And why exactly bit flips? Like, why not something else?
Okay, so you mean like why go for something bit?
Yeah. It's like very detailed, like attack. It was like it's a system generated thing, like generally it sounds like, but like how can why would someone want to just do flips?
It's actually kind of loaded, right? I mean, especially before the base, I think the base scenario is actually most heavy. You can go into base information is hard to change if I did so. It depends on the attacker's mode.
I want to get access.
On admin rights.
It depends on the
that your original data first. Okay.
President tries to I'm working 8. This will correct that. If easy can do is correct, and easy to do it, right? And Copy-on-Flip works on page level. So the page consists of several easy sequences, right? Once there's a bit if somewhere, this will correct it. And Copy-on-Flip back to that. That's one sense, right? Now, try to want another bit somewhere in the page, right? Then it will also correct itself. Now this page is so it corrects it, copies the entire but it doesn't copy the
Okay. Okay, so it realizes that the page is like under attack, like it's vulnerable, so we don't want to like keep it here.
Yeah, that's perfect.
I have a question. Like you told, like when we are doing the mitigation, we stop all the alteration in the memory. Yeah. So, like, what happens to the processes which are going on, or all the requests which comes to the memory at that time?
very interesting. This in the paper, they don't really, and I think it's because it is a very fast process, right? Like, I think working at that sort of level, it's not this. It's transferring page should be very consistent. One thing you should actually cause the overhead or do the because even if you look at the evaluation, there is a little bit of cooling, right? So I'm probably thinking that might actually, the fact that we stop correct, it actually cause a little bit of effect. Not too much. I think if a request comes in, guess that's to stay until all the requests are active. That allows people to work from their home and maybe another frame like that. That's a very good question. This is like no one's buy like you buy a memory, right? What can you do? Right now we copy on the option for that. Or how big right? So that is one side downside of copying, right? All the memory rows are getting uptime. You can't reclaim them back. But drop the bullets out. Once you do it, everything is done.
We'll go into discussion really quick. So why does MCopy-on-Flip rely on memory error correction? But then instead of trying to detect Rowhammer activity directly to hardware on it. This is a question to the audience. You can cookies, but if you're able to answer it.
I'm pretty happy. The granddaddy of the page. Granddaddy of the page that we have.
So basically those granular lines that I went over, that's basically why we rely on that. Okay. Okay. Okay.
One more question, please.
Good. Yeah. What's the purpose of the template?
Last question. So guys, giving you all.
Take that way carries some action solving. Because Rowhammer is actually because of the scar you have density, right? The chips are very close to each other, right? If there's a way to sort of like keep them apart physically, then I guess maybe you might solve. I don't think companies are very greedy. They want to pack a lot of things.
Yeah, I don't think that's why. Yeah, they're having more games. But it would be hard to kind of actually physically separate them. Space. Okay. Users are hungry for money. More memory you have, the better. I don't think it's going to be solved, but hopefully we'll see.
There's a recent paper. How long? So the memory cells smaller. Right, thanks so much, guys. So we can take like 4 minutes.
Yeah, I'm going.
So let's take 4 minutes quick break. Then we'll be back. So we'll prepare for the next talk. Test, test, test.
Khalil. Khalil here.
it works.
Say something.
Test. I don't know whether it's work.
Say something.
Okay, test. Mhm. Test.
Blinking. Test. Keep blinking. Everyone does laptops. No laptops at all. This includes phones as well. Don't hide it.
Okay.
These are markers.
Okay, thank you. Okay. Okay, let's get started. Like after listening to a really wonderful presentation of the last group, let's start ours. So today, our team is going to present a paper which is called Hertzbleed. And I will present with my teammate, Zhang, and my name is Ning Yan. Okay. So this paper is about side channel attack. Is there anyone like whose research is about like cybersecurity or take some courses about security? No one? None of all you? Okay. So is there anyone who might know that what is side channel attacks? Who answered? Okay, you can get one. Okay. Before we start, we'll let you know what is side channel attacks. Let's have a look at the modern computer architecture diagram. But besides the computer doing the computation, it also makes some byproducts like the instruction timing and the branch behavior on the cores, and also the hit or miss timing on the catches. And even the EM and the voltage swings on the memory bus. Also the EM voltage swings on the NIC GPU and the disk. And the current and voltage on the power rail. And the EM and the voltage on the clocks. So there are different types of byproducts while the computer do the computations. So all of these observation features are different types, such as the power, the current, and the EM, and the time or the latency. and also the catch hit or misbehavior. So all of these observable artificials are the source of the side channel leakage. That is called the side channel. It's the byproducts the computer hardware architecture made while doing the computation. So here comes the concept of the side channel attacks. The side channel attacks is the computer hardware leaks information through all these byproducts we have mentioned on the last slide. Let's start with a really simple example. Here is the EM side channel from the data bus. And there is a motherboard. And there are two components here, components A and components B. There are two components on the motherboard. The components A and B communicate with each other using the data bus. And when the components A and B transfer the data, there are some like base transferring, and it may cause the EM, and then we can put a prop nearby the data bus here. Then the prop can catch the EM signals from the data bus. This is the first step of this side channel, which is called coupling. The prop picks up the EM signals from the data bus. And after this, here comes the second step. It's the measurement. The prop and also with the ADC can record the EM waveforms. This is called the measurement. And then come to the third steps is alignment. If we use the prop to record the waveform, if we only do one capture, this capture maybe is with enough noise, we cannot use it. Like the attackers will do it times and times again and collect a lot for not a lot of times, and then do the alignment. The alignment is line up all the traces we record in the time using a trigger. So that's the third step is alignment, and then comes to the next step is the feature extraction. We can see that's what we get. So we can identify the patterns, and these patterns will relate it to the data activities inside the motherboard, inside the data transferring between the components A and B, and we do the feature extraction. That's our fourth step. Okay, after this, we come to our next step. It's the inference. We can translate those patterns back into possible bits. So we can like get the 1101, and this is 1011. So we can translate these patterns back into possible bits. Then we can get what's the data inside the motherboard are transferring. That's a really simple example of the EM. After the example, let's talk about the classification of the side channels. we can divide all these side channels to different types. The main type maybe the power, like we can use a prop, place a prop on the chip and record the waveform. And then the EM, we can also like play a prop nearby this chip and record and do the bus coupling. And even we can record the time, the execution time, how long does the program like finish, and even the cache. Here is an example. There are two VM. This one is attacker and another one is victim. They are sharing the CPU caches, and this attacker can use the cache hit or miss time to detect what the victim, what's the data the victim is accessing. And we can also like listen to the sounds, like the noise of the HDD. So that's the main types of the classification of the side channels: the power, EM, timing, cache, and even the sound. Okay. Besides the side channel types, the most important of them is the power side channel attack. And this paper, Hertzbleed, is talking about how the power side channel attack changes to the time side channel attack. So let's talk about the power side channel attack first. Okay. Like we can put a prop on the power rail and use the ADC to record the EM. Like there are transferring inside the crypto core, and we don't know what's the data inside it. But after we use the prop and the ADC to record the information on the power rail, then we can change the power information to the peaks like this. We can get the data dependent peaks. So after doing times and times again and do some analysis, we can get the information from the data dependent peaks and infer what's the data inside the crypto core are processing. So this is the power side channel attack. Because we are collected the prop on the power rail, so it's also called the no-call or call-resistant attack. And it requires physical access because we need the prop to connect the power rail. And we also need some tools like the prop and also like the ADC. Because we need to physical attach on the prop with the power rail, so it has a high detection risk. Different with the power side channel attack. Here comes the time side channel attack. Time is like how long does for the program to execute. for the program to finish. For example, there is a code segment. If bit equals 1, we will do A, else we will do B. So then it will jump to different paths, path A and path B. It will take different times for the path A and path B to finish. And the remote attacker can record the time difference of the path A and path B through the network without using a probe to connect with the hardware. So the timing side channel attack is also called remote attack. There is no physical access needed. So because there is no physical access to needed, so it's easy to deploy widely. And we don't have to use some tools like the probe or the ADC. We just need to record the time. So, and we don't even need the physical touch with the physical connection. So it will have the no detection risk. Because it can do through the network, so you can target for multiple victims. That's the difference between the timing side channel attack with the power side channel attack. As we have talked on the last two slides, right? The power side channel attack is the local attack because lead physical connection, lead tools, and it has high risks. So it has no efficiency. But for the timing side channel attack, we can do it remotely. We don't need too much tools. We don't need to connect physically. So it has the high efficiency. So the underlying of these two principles is similar. There are some data transferring, like the switching of the signal inside the cockpit core or the code, and then it can change to observable informations like the power on the power rail and the time of the different execution time of path A and path B. And then we get all this information, we can do the statistic inference. We can, without knowing what are doing inside the computer core or inside the code, we can also get the information inside it and do this kind of an attack. But the difference between these two attacks is whether we can do it locally or we can also do it remotely. That's the difference between these two. So here comes the key question. If the timing that channel attack is more easier and have a high efficiency, whether we can change this power side channel attack to the timing side channel attack. That's the key question of this paper. Then here comes to the key insights. Does anyone have a guess whether it can work? Like we can change the power side channel attack to the timing attack? Just have a guess. Yes or no? No?
Because when we look from frequency standpoint in the system.
Oh yeah, you know it.
Time
Yeah.
and then. Thank you.
So he got the correct answer. But why is that? Let's talk about it. Okay. On the main insight of this paper is the dynamic voltage and frequency scaling. It is the computer can dynamically adjust the voltage and frequency to balance the performance and the power. And it is workload based. It means the CPU can adjust the voltage and frequency because of based on the workload. We can see from this figure. If there is on the left side, if there are higher workload, it will get the higher voltage and frequency, which is called the max tube state. And the right side is the lower workload. It leads to lower voltage and frequency. It's called the steady state zone. So because of the DVFS, we can know that the CPU can adjust this voltage and frequency, this depending on the workload. And how these changes can leak secrets. So here comes to the assumption. I have my. We already know that the data can lead to the power. And because of the DVFS, we also know that the power can lead to the frequency change. And when we also know that frequency can lead to time, right? So if we can like collect like this, so we come to an assumption whether we can use time to detect to get the data, information, right? That's our assumption. So from the left side of this figure, we can see that the power consumption will change with the data. We can see there are different workloads, and the power consumption have different distribution. And as we have talked here, since the DVFS adjusts the frequency based on the power, so it comes to the assumption whether the frequency itself can also carry the data-dependent characteristics. That's come to the main assumption of this paper. Here is the verification of this paper. They did experiments. If they only change the data values being processed, it's the input. We can see from this figure, there are different input, 1, 2, 3, and the x-axis is the power consumption, and the input is different. The distribution is different. That is what we have already know. The input is different, the data is different, the power consumption is different. after we can see from the right side, the experimental results show that the CPU frequency shows the corresponding patterns, like the power consumption as well. So it verified our assumption of this one, right? So why is that? Why is that? Why is that? Do you know that? Why is that? Like, it's because two main factors, like the Hamming distance and the Hamming weight. What is the Hamming distance? Is how many base flips inside the binary value. Like we can see from here, the AX is like this, and it changed to this. So how many bits have flipped, have changed? There are 10. So the Hamming distance is 10. And for this example, the AX is like this, and it changed to like this afterwards. And there are only 6 bits have changed. So the Hamming distance for this one is 6. So the Hamming distance of here is smaller here than here. So this one has lower Hamming distance. Then it has lower power consumption, and then comes to higher frequency. And the experimental results also shows that the x-axis shows the count. The higher count values means higher Hamming distance inside the ALU output. So we can see from the left side, as the count increase, as the x-axis increase, the Hamming distance is increased, and the frequency is keep going down. But on the right side, the power and the count, as the x-axis is increased, the count is going bigger, and the Hamming distance is also going larger, but the power consumption is going increase. So we can see that as the Hamming distance increase, the power consumption grows, but the frequency drops. So here comes the question, like why higher Hamming distance leads to higher power consumption? Oh, yes, you can get one. So because we have talked about the Hamming distance is how many bits changes inside the binary value. If it's changed more, it will lead to higher power consumption. Okay, after talking about the first factor, the Hamming distance, let's talk about the second factor, the Hamming weight. We can see from this figure, the A shows the frequency. How does the frequency change with the Hamming weight? And this shows the power changes with the Hamming weight. The higher number of, so here comes what's the Hamming weight? It means how many ones inside the binary value. Higher Hamming weight means higher number of ones inside the value. So we can see from this, from the experimental results, the Hamming weight increase the power consumption grows and the frequency drops. So after talking about this, we know that how the power and the frequency changes with how many ones inside the value and how many bits flips inside the value, right? And there is something we also need to care about. It's the bit position. So we can see from this example. On the upper one, the AX is like this. So there are like 8 ones inside this value. So the Hamming weight is 8. And this one, there are also 8 ones inside the value. The Hamming weight is also 8. So they have the same Hamming weight. And we do this computation, the same computation. They are doing the same times of base flip. So they have the same Hamming weight and Hamming distance. Whether they have whether they have the same power consumption and the same frequency changes. Have any guess? It's different or the same? It's different. Why it's different?
Because of the switching activity associated with either nibble side of the bits position.
Oh yes.
I think it's the LSB or the MSB side of it. MSB will have generally.
So this one will have even though these two have the same Hamming weight and Hamming distance, this one have a higher frequency. So here comes the question. Anyone else want to answer? Like why higher order of bits consume more power?
Because it will higher Hamming.
If they have the same Hamming weight and Hamming distance, but the bit flip in the higher order, why it consume more power? Oh yeah. That's because the higher order bits consume more power because they drive longer and heavier paths. There is another experimental results that shows we can see the x-axis shows the byte index, and the y-axis shows the frequency and the power. We can know that if each time we only set a single byte of to this value inside the input, and we change this index, this byte index, or this and this byte index for each time, and we get the data, the results like this. So we can see from the results that the Hamming weight difference in MS, like in the higher byte index, it has stronger effects, but in the lower index, it has the weaker effect. Okay, this change slower, but this change faster and stronger from the higher inside the higher index.
Okay, so as Ning mentioned before, we can have this inference like a dominoes chain. We know the data, we know the power. We know the power, we can infer the frequency and the time. So you can see with different time, if the frequency is different, also the time is different. And so as mentioned before, we can converting power. We know the power information, and then we can infer the time information. So it is like a domino chain reaction. CPU process the data, and because the CPU process data like the bits, they have zeros, they have ones, and they are on different positions. So the power consumption changes. And after the power consumption changes, the DVFS, the function, will adjust the CPU speed. Has anyone still remember what DVFS is? The full name of DVFS?
Dynamic voltage.
Yes, and did you notice that when you turn on your computer, the desktop can you see? Yes, in the BIOS, like turbo. Yeah. And then because the CPU speed changes, the frequency changes, so the execution time changes, and then the attacker can measure the time without knowing the time, but knowing other factors like they know the frequency, and then they infer the time information. So here comes Psych. So Psych is a very famous crypto algorithm had been used for decades, years. Like it is public key encryption scheme used to secure a shared key. Like this paper was published in 2022, and Psych, although it had been used for decades, years, but in 2023, due to different leakages, it was not used anymore. One leakage is like this side channel attack. So for Psych, there are three. It is like a 3-point ladder. First, it loops the secret key bit by bit, and in every loop iteration, it has a data flow depending on the current secret key and ciphertext. And if the attacker knows the secret key based on it, the attacker can come up with a ciphertext. So it is the idea of this paper, like how attackers can leverage ciphertext to hack the Psych. Like every user can send ciphertext to Psych. It can be a normal user. It also can be a malicious user, a hacker. So like how this paper do side channel attack. So like an attacker who knows the least significant bits of the key can construct the ciphertext, the malicious ciphertext C prime. Like if mi not equal mi minus 1, which means like for example the first bit is 0 and the second bit is 1, and then it means different. The data flows change, and the Hamming weight, the Hamming distance changes. They decreased, and there will be lower power consumption, and then higher frequency, lower runtime, and vice versa. Data flow does not have a low Hamming weight or distance, and high power consumption, lower frequency, and a long runtime. So this paper also implement this assumption how to against Psych. The goal is to demonstrate that the frequency side channel is a real threat, like not only existing in assumption, but also in the real world. Therefore, the attacker use the method mentioned before, the frequency side channel, to hack the Psych. So using chosen ciphertext attack, where the attacker sent the ciphertext to the Psych key, and to demonstrate that the implementation is on two mainstream platforms, which is Cloudflare. I think everyone knows this brand. Cloudflare interruptible reducible cryptographic library cycle. It used Go language and Microsoft PQ PQ crypto SIDH, it is in sign language, and both runs in constant time. So as mentioned before, what is the vulnerability? Like the attacker sent the malicious ciphertext to site and to get the data information. If the first bit is 0, and then the continuous bit, there will be random numbers. Therefore, you can the CPU to process such data, the CPU cost much more time. And if the first bit is 1 and it generates only zeros, and of course the CPU doesn't take too much time, so there is significant time difference between 1 and 0. And as like before, if the first bit is 0, like A means the time, and R1 means like a positive number. So of course it costs more power because it has lower frequency and it has longer runtime. And if the first bit equals 1, like and then the second bit is 0, and then 0, 0, 0, 0. So less power, higher frequency, and shorter runtime. So this paper implement and demonstrate that on Cycle and the PQ crypto platform, and the results showcase that the assumptions are right. You can see the blue ones are zeros and the red ones are 1, so significant time difference. And to revert the 4K on Circle, it used 36 hours, and to recover the 4K in PQ crypto, it used 89 hours. It's considered a long time, but still they attacked successfully. So that previous attack are based on time, but it can be like, as mentioned before, it is like a chain. So although we don't know the time, if we know other factors, like we know the power or we know the frequency, we can also know the data, right? So to verify this assumption, the attackers also use 2 side channels without time, but like use side channels. So they called castle break and convert channel. So they use different channels, but also the result shows like on I7 the successful rate is very high. Like one is 1010 and another is only 0.03% error. So here are the paper's takeaways. This Hertzbleed attack can affect CPUs, Intel CPUs from 8th to 11th generation of the core micro architecture, and Intel Xeon and AMD Ryzen processors can also be affected, but they are not affected to older CPUs. Can anyone come up with the reason why it affects to 8 to 11 generation, but not affect older generations? Any answers? Okay, so because the older generations, they don't have the DVFS function. It is a new function. So like the function brings like also new leakages, new vulnerabilities. So to mitigating the leakage via frequency channel, they have several mitigations like restrict CPU, like turn off the DVFS function, also called turbo boost or speed step. It is in different brand, I think, so different name, but the code is the same. And also mitigating leakage in ciphers, preventing cipher attack from triggering a secret dependent computations on zeros, mitigate the power leakage. So here is the conclusion of the paper. DVFS cause CPU frequency to vary with power and sort with data. So like, as mentioned in this dominoes chain, we know the data, we know with the time we can know the data. And also this paper proposed demonstrate this assumption with their real-world implement, and also they also demonstrate how on other side channel attacks in this chain, and also they proposed how to mitigate this. So I think it's your friends.
Let's talk about my opinion on this paper. I think this paper, the most important one is the novelty. So it comes up to the DVFS, the frequency change with the power to it's novelty. It comes up to this the DVFS, the frequency can change with this power, and then we can do the side channel attack with the time and the frequency.
So it is a new attack from a lower level, having weight and distance based decay, and it escalates to end-to-end key extraction from SIKE. It was the most popular encryption algorithm then, but not now because it was hacked, and it breaks the old belief of constant time code is safe. Like we can say the constant time code, it is not safe due to we can use the malicious cipher attacks to get the data to get the data leakage. So there are also some limitations. So first, if real computer or service, there is noise from the main program running at the same time, so the time signal becomes weaker and slower to detect. For example, if you have a computer with you have no program run on it, so of course you can get the ideal, like it is like an ideal experiment environment. But imagine that you are running deep learning models, you are running a lot of programs that cost a lot of computational resources. So you can see the voltage might be not that stable, and then it will get a negative influence on this inference chain. So the inference, if on the real world with real program running, so the result might not be that accurate. So also it is not applicable to old generation GPUs due to the DVFS, and also the attack was timely. So after that, maybe also after the manufacturers realize this leakage, they may also do some updates on the DVFS algorithm, and then the leakage cannot be used anymore, and it takes too much time of queries against the stable security key as mentioned as shown before. It took 36 hours and 89 hours. It considered a very long time. It might be not, but it might not be a limitation anymore in the future because the quantum computing or something we don't know, or the higher computational resources. So here are questions. So why is Hertzbleed dangerous even though can't measure power remotely? Any answers, volunteers?
The speed at which the data is traversing and still figure out rate at which the system is operating. Speed at which data is transferring that. To somehow calculate power based on that.
to show the answer.
See the answer from here. Like even though we cannot measure the power because the DVFS, the frequency can change based on the power. Then we don't need to measure the power. We can measure the frequency, even the time. Instead, measure the power to get the information to do the side channel attack. So the main idea of this paper we can see from here. Just remember here from here, like the data, the power will change with the data. And because of the DVFS, the frequency will change with the power. And then we can, through the frequency and the time, to do the side channel attack, even though we don't know the power, what the power exactly is.
So here is another question. If you are running if your crypto code is considered time, do you still consider it as safe or not? Like it is mentioned before in the discussion page. Okay, no answer. So it is not safe because there are different vulnerabilities. They can not only DVFS, but also like hash, the branch, the TLB, the HMT, shared codes. They are all set channels to hack the constant time safety. Another question, if an attacker can send chosen input repeatedly to a long-lived key over the network, what prevents his Hertzbleed style attacking your setup? Rotation, rate limiting, isolation, no DVFS? No answers. So there are time access pattern, control, isolation, deploying frequency, power behavior. They are all potentials to tackle this question. So another thing, it is about what kind of other side channel attack you can imagine, not limited to CPU, but also other components or anything you can come up with, like side channel attack.
Temperature at room temperature.
Sorry, say it louder.
Room temperature might impact.
Yes. Yeah, so side channel is everywhere. Like since data is everywhere, so there are a lot of side channels, like cache-based branch predictor, images, and also, for example, you can in real world, some people they can even use Wi-Fi signal to detect human movement, or they use microwave to detect like food temperature. So signal is everywhere. Data is everywhere. So thank you. So here is the discussion. Do you have any questions for us? Okay. As you mentioned before, just turn off the DVFS. Like in this paper, you already have the solution, or restrict the CPU.
No, but given the steady state run, right? Given steady state run in any machine, why we have DVFS at first place is, imagine any application which starts, so it goes up, stays there at the top because it's doing that internal critical functionality, and then come down. Why we have DVFS is to mitigate this peaks, both the sides, right? If I understand correctly. Now you cannot disable DVFS just to address this, right? Otherwise you're running at a constant speed, and that the very nature of DVFS you have removed, and hence you don't have this new capability of having to have efficient system, right?
You're right.
Yeah. Now the problem is, if you remove DVFS, removing DVFS is not a solution at this point. Should not be also.
see. Yeah, you are right.
You are in I14, I13, but you are taking me to I7 back, right? To remove DVFS effectively.
Right.
For example, you're from I while you are
Right.
The data center always runs.
Yes, there are multiple voices.
That's true. Some scenario there.
Is it possible, like, because it is like a chain, data to power, power to frequency, is it possible, like, use some encryption on this chain, or like use, like, for example, or generate some synthetic data to mislead the final output?
And then we call function. Right?
Yeah.
So you add your own code, and then whatever you want. Then you control your ID. Data.
Thank you.
Think like whole research area. Hardware. Where privacy is not protected. Or like ID.
Yes.
They're not doing. Right. Those were really interesting topics. We see a lot of Rowhammer. Because we need a lot of software really hardware. Actually. Some like very typical some of them like coming more and more coming really thank you so much.
Thank you.
Time to vote. So I think Supper did a great job. He already posted the results of the voting for the first 3 weeks. So if you are curious, go to iCollege, go to the schedule. You'll see the results, who are the winners among the teams and how many votes per time. We'll continue doing that for the rest of the semester. Okay? Yeah. Please send your email right now within 1 minute. If you exceed the 1 minute, we consider it absent. CC Supper as usual. And thank you so much. We'll see you next week.